Earlier in this lecture, we just talked a lot about the synthesis and reactivities of pyridine. So from now, let's talk about the analogs of pyridine, which are quinoline and isoquinoline. So let's have some recap about the reaction of pyridine. We know that pyridine is less susceptible to electrophilic substitution and more susceptible to nucleophilic attack because it has lower electron density than that of benzene. So if we react pyridine with electrophile, it will substitute at the beta position due to the resonance effect. And we know that you can oxidize pyridine with peracid into pyridine N oxide, which has its own unique chemistry. If you put some alkylating agents, it will go on the nitrogen. And if you put some acid, it will protonate the nitrogen. Okay. And if you react the pyridine with a strong nucleophile like sodium amide or N-butyl lithium, it will directly attacking at the alpha position, but you need to have some hydride transfer to something else. This reaction I didn't mention is the reaction with radical. The radical will attack at the alpha position to substitute the hydrogen, and you can fully reduce the pyridine into its fully saturated analog using hydrogen platinum. If you look at quinoline instead, it is the pyridine fused with benzene ring. The key difference between quinoline and pyridine is that when you do electrophilic substitution, it will favor the reaction with the benzenoid ring rather than the pyridine ring, because the benzene ring, when the quinoline reacts, the pyridine ring has higher electron density, because in the pyridine ring the nitrogen pulls away electron from itself. So the reaction will occur at the C5 or C8 at the benzenoid ring. So this is the most important difference between quinoline and pyridine. And because of this, quinoline is more reactive towards electrophile, although still much less than benzene itself. And most other reactions are the same as pyridine. For example, oxidation into the N-oxide species, alkylation with alkylating agents and some acylating agents, reaction with acids, the direct addition onto the alpha position, and reaction of radical at the alpha position, and fully hydrogenation of the pyridine ring using hydrogen platinum. The reason why it prefers to react at the 5 and 8 position is that when you react at the 5 position here, you are going to generate the positive charge at this carbon, which can delocalize onto the second carbon here. But if you react at the 6th position, for example, the positive charge here cannot resonance unless you are going to break the aromatic system of the second ring. So this resonance is not good because your second aromatic system will be broken as well. For the synthesis of quinoline, I'll just show you some examples of named reactions. The first reaction is Krupp reaction, where you heat the aniline with glycerol under acidic conditions, and you need to put some oxidizing agents like some nitro compounds as well. So first of all, under acidic conditions, the glycerol will be converted into acrolein. So you can remove this water into And from here you can also remove another water, and this will lead you to the formation of acrolein. Formation of the acrolein here. So this is the real electrophilic species that the aniline can use the nucleophilic nitrogen to attack at the beta position, the conjugate addition. After that, you will generate the aldehyde at the terminal position, and from here the aniline can use the lone pair the electron in the electron rich system attacking at the aldehyde, and then you cyclize the ring and regain the aromaticity to form almost becoming the quinoline structure. And after that you need to oxidize using some oxidant into quinoline. Okay. The second reaction is very similar to the previous one. In this case, you use the alpha-beta unsaturated carbonyl compound as the electrophilic reagent. So reaction between anilines with, by conjugate addition, and then after that you generate the terminal aldehyde here that can react with the nucleophilic ortho position of the aniline to forms the after elimination you form almost becoming the quinoline, and then you do oxidation to make the aromatic system quinoline. The next example is the reaction between anilines as a nucleophilic site and the 1,3-dicarbonyl compounds as an electrophilic species. The reaction will proceed by reaction between amines and the first carbonyl group under acidic catalyst. So this will lead you to the formation of enamine, okay, and from here you can use the ortho position of the aniline, which is quite nucleophilic, to attack the ketone that it formed. This will lead you to the cyclized product. Okay, and you have the proton here. This can regain the aromaticity by removing the proton. And in this case, you don't need to use the oxidant because you already have the leaving group as the OH. So this lone pair from nitrogen can attack and kick out the OH as water. So finally you will generate the quinoline from this condensation reaction. In the last example, this is the synthesis of isoquinolines, where you do the condensation between benzaldehyde, which is electrophilic at this carbon, and you will later use this carbon as a nucleophile. And also it will react with the 2,2-dialkoxyacylamine, where this is your nucleophilic site and this is the electrophilic site, okay, under the acidic catalyst. So the first thing it's gonna do is the reaction between the amine with aldehyde to form imine. Okay, so if you draw this structure mechanisms, you are going to form the imine, and the acetyl group here can be cleaved under acidic conditions, and you are going to form the electrophilic oxonium species here. that will facilitate the ring cyclization, the nucleophilic attack from the aromatic system. And from here, you can regain the aromaticity by removing the proton. And since you already have the leaving group, so you can kick out the leaving group to regain aromaticity. And here you got the isoquinoline as a product. Finally, I would like to show you the notable synthesis of pyridine containing molecule. The pyridoxine is a vitamin B6 containing pyridine, and it can be synthesized starting from the 1,3-dicarbonyl compounds as the electrophilic sites. And in this molecule, you have this carbon that can tautomerize to form enol, which is nucleophilic. And you can use the lone pair on the nitrogen to be the nucleophile as well. So after ring closing condensation, you will form 2-pyridone as a product. And by using nitric acid with acetic anhydride, you are going to form the nitrating electrophile NO2+, which can be attacked by the beta position of pyridone. And after rearomatization, you will get nitro group at the beta position. And I already mentioned in this lecture that 2-pyridone can be converted into the 2-chloropyridine using POCl3. After that, you can use hydrogenation to convert NO2 into NH2 and convert cyanide into CH2NH2 and the chloro into hydrogen. After that, they put sodium nitrite to change the NH2 into diazonium salt, which under aqueous condition, this will become phenols or alcohols here. Okay. After that, they put HBr under heat, which will protonate here, and the bromide comes to attack to make the CH2 bromide. And using silver chloride with water here will make the bromide as a good leaving group, silver bromide, and the water comes in to attack, and you got the alcohol here. And you finally, this is a vitamin B6 pyridoxine. The next example is chloroquine, which is a synthetic antimalarial drug. First of all, if you use aniline, which is nucleophilic here, with the 1,3-dicarbonyl compounds, but because this ketone connects to the ester group, this is more reactive. So the first thing that's going to happen is the nitrogen attacking this more electrophilic ketone to generate enamine. And then after that, you can use the ortho position of the aniline to attack another ester group here, kicking out OET as a leaving group. At the end, you will form the 4-quinolone as a product. And after that, you can remove this ester group by reaction with base under heat, 270 degrees. So the base will hydrolyze the ester to form carboxylate, and then the carboxylate will decarboxylate, and then you can remove the ester group. Okay, and we know that the 4-pyridone or 4-quinolone can react with POCl3 and then the chloride comes in to attack here, and then you generate the 4-chloroquinoline, which is now can behave as a leaving group. And from here you can use the nucleophile, which is the primary amine here, to attack at the 4 position, kicking out the chloride leaving group, and then you form the new bond between carbon and nitrogen here, which give you the chloroquine as a product. So for the homework, please send this in the blackboard